Hey everybody, today we're getting into random variables. Random variable is a variable defined by a random process. So there's some sort of probability experiment going on. The outcome is a number. We're going to call that number the value of the random variable x. A few examples make this very clear. You roll 2 dice, you take the sum. That's a random variable. You flip a coin 50 times, you count the number of times you get heads. You pick a random person in the city of Chicago and you measure their exact height. And you go and measure the length of an eruption of the Old Faithful geyser. Just for contrast, let's mention a few probability experiments with outcomes that are not random variables. The gender of a randomly selected puppy at a dog shelter, the eye color of a randomly chosen U.S. senator. So here we have random processes, but the outcomes aren't numerical. These are categorical data, so they are not defining random variables. There's 2 fundamental kinds of random variables, discrete and continuous. Continuous random variables take their values in some range, like the exact length of an eruption or the exact height of a randomly selected person. So when I say a range, I'm meaning including fractions, decimals, as accurate as you like. In contrast are discrete random variables, and there you have random variables whose outcomes can just be listed, 1, 2, 3, 4, 5. Some examples: the number of heads the number of heads that come up when you flip a coin 50 times, or the sum when you roll a pair of dice. When a random variable has a finite number of outcomes, of possible outcomes, you can just make a table of all those outcomes and their probabilities. That's called a discrete probability distribution. Here's an example. Flip a coin just 3 times and count the number of heads. You can get 0, 1, 2, or 3 heads, and we have probabilities for each of those. So there's a 1 in 8 chance of getting no heads, and on down the line. Hey, by the way, here's how I came up with those numbers. I just listed all the different possible outcomes when I flip a coin 3 times. And then I said how many of those 8 possible outcomes fall into the category where I have 0 heads, how many fall into the category where I have 1 head, and so on. So 8 total outcomes, and then 1 possible way of getting no heads, so a 1 in 8 chance there, and so on. Again, this table that I have at the top half of the slide is called a discrete probability distribution. Discrete probability distributions can come directly from data, as in this example. A random sample of 100 adults in the United States is asked, how many times did you eat dinner out this week? We get responses between 0 and 5. So now suppose we go out and pick one person from that sample at random. We can get the probability that they said 0, 1, 2, 3, or 5 by 1, 2, 3, 4, or 5 by taking the number of people in that sample that said yes in each of those categories and dividing it by the total size of the sample, 100. So for example, the probability of randomly selecting someone that did not eat dinner out at all last week is 49 in 100. 100 total people, 49 people that did not eat out last week. If we do that for every one of those 6 categories, we get a probability distribution right here. All of the possible outcomes of the random variable x and all of the probabilities. So just as we can draw histograms to visually represent frequency distributions, we can draw probability histograms to visually represent discrete probability distributions. So keeping up with this same example that we started on, where we have the number of times 100 people have eaten out in the past week, and the probabilities, we can draw a histogram like that. So I label 0, 1, 2, 3, 4, and 5, and I draw bars for each one where the height is the probability. So for example, for x equals 0, 0 meals out in the last week, I've drawn a bar of height 0.49. Of course, if I drew a frequency distribution for that same data, the shape would be identical.